This section focuses on considerations for optimizing container workloads within Azure, emphasizing the importance of selecting the right resource configurations and scaling patterns to meet application demands. Building on prior modules about Azure Resource Manager templates and container provisioning, we now explore how memory, CPU, and storage requirements interplay with performance and cost. Understanding how containers respond to real-world loads helps ensure high availability and reliability. In Azure Container Instances, ACI, and Azure Container Apps, sizing and scaling are particularly relevant for ephemeral or microservice-based applications. By aligning resource usage with anticipated traffic, organizations can keep costs under control. Containers encapsulate applications alongside their dependencies, which allows for simplified deployments and consistent environments. In Azure deployments, container resource requirements typically revolve around CPU cores, memory, and ephemeral storage. Requesting the right resources ensures that each container can handle peak loads without interruption. Conversely, setting excessive limits can inflate costs or exhaust cluster capacity. By analyzing application performance indicators, administrators can forecast usage and allocate resources prudently. Furthermore, Microsoft Azure supports ephemeral disk storage for container logs and scratch space, essential for applications needing temporary data. Thus, resource planning directly influences service continuity and cost efficiency. In platforms like Kubernetes or Azure Container Apps, administrators define container resource requests and limits to control resource allocation. Requests signify the guaranteed minimum CPU and memory that a container will receive, ensuring stable performance even during high load. Limits represent the maximum resources a container can consume, preventing excessive usage that could disrupt other workloads. Properly balancing these values aids in curbing cost overruns while still satisfying demand. Overly restrictive settings might degrade performance, whereas overly generous limits risk idle resources. A well-tested approach involves gradually adjusting values in alignment with observed metrics and throughput demands. Azure Container Instances, ACI, enables seamless scaling of containerized applications. Using the Azure portal or command line tools, administrators can specify the number of container replicas based on workload requirements. Although ACI does not natively offer auto-scaling, manual adjustments are straightforward, allowing organizations to react quickly to changing traffic. When multiple containers run within an ACI group, each instance may define its own resource limits, ensuring precision. This approach suits scenarios requiring on-demand bursts or ephemeral tasks. For more advanced scaling, external triggers or orchestrators like Azure Logic Apps or Kubernetes can help automate instance count changes. Azure Container Apps extends container orchestration capabilities by offering integrated auto-scaling through the Kubernetes-based Kata framework. It continuously monitors metrics, such as message queue length or CPU utilization, to dynamically adjust container replica counts. By responding to real-time usage, container apps can rapidly adapt to spikes or drops in demand, preventing slowdowns or idle resources. Administrators can define scale rules based on triggers like HTTP requests or events from Azure Event Hubs. This event-driven model suits microservices architectures and serverless patterns, where scaling is often unpredictable. As a result, container operations can remain agile, cost-effective, and responsive. Azure CLI and PowerShell provide convenient methods for managing container scaling. Administrators can script commands that adjust instance counts or resource limits without relying on the Azure portal. For instance, using Azure CLI, one can update an Azure Container App Scale settings through commands referencing CPU or memory metrics. Such automation is valuable for continuous integration and delivery pipelines, where container scaling requirements might evolve frequently. Additionally, edge cases, like restricting container restarts or reducing replicas during maintenance windows, can be scripted. By centralizing these commands, teams gain consistency and reproducibility in their scaling strategies across different environments. Many modern solutions utilize multi-container architectures, often arranged in microservices. Within Azure container instances or container apps, these solutions can be deployed in groups, allowing each container service to address a distinct function. Resource sizing becomes more complex in this context, as administrators must coordinate CPU, memory, and storage across multiple containers within a single environment. By monitoring consumption patterns, teams can allocate capacity precisely while minimizing waste. Furthermore, container-to-container communication can impact overall resource usage due to factors like network overhead. Conducting performance testing on each microservice ensures the right scaling decisions, optimizing throughput and resource efficiency. Effective container sizing and scaling rely on continuous performance monitoring. Azure provides tools such as Azure Monitor and Application Insights, which offer real-time visibility into CPU utilization, memory usage, and response times. By analyzing historical data and setting custom alerts, teams can proactively address potential bottlenecks or excessive resource consumption. Logging frameworks also highlight container restarts or error rates, signaling the need for adjustments in resource allocation. In multi-region or distributed deployments, aggregated metrics across locations reveal variation in demand. By leveraging these insights, administrators can tune container sizes and scaling thresholds for reliable, high-performing applications. One frequent challenge is overestimating resource requirements, leading to unnecessary costs and underutilized compute power. Conversely, under-provisioning can result in performance bottlenecks or application downtime, especially during sudden traffic spikes. Another mistake is ignoring transitional states, such as container startup times, which may temporarily require extra CPU or memory. Failing to correctly set resource limits can allow a single container to monopolize the host, affecting other workloads. Also, neglecting performance metrics or alerts can lead to delayed responses when usage patterns change. Ensuring effective governance, thorough testing, and ongoing monitoring helps mitigate these risks and maintain application reliability. When planning container sizing, start with resource profiling to establish baseline CPU and memory requirements. Gradually introduce scaling policies after validating workloads in realistic test environments. Leverage built-in Azure monitoring to detect spikes and configure auto-scaling thresholds that align with business goals. For multi-container applications, dedicate ample resources to critical services while leaving headroom for shared processes like logging. Use container orchestration solutions, such as Azure Container Apps, to automate vertical and horizontal scaling dynamically. Document sizing decisions, rationale, and monitoring strategies for future reference. Ultimately, consistent review and iteration ensure that container resources remain tailored to evolving demands.